on the left-hand side of the screen, that formula that I have highlighted is the formula. It's kind of a definitional formula. It tells you the definition of voltage or potential difference is the ratio of the change in energy involved. The change in energy involved as a charge moves from one place to another to the charge. And if you go back and look at yesterday's notes, we started off by talking about pushing a charge to where it does not want to be, and that change in energy was potential energy. We did work to the charge to give it potential energy. And if you divided that potential energy by the charge, you got what's called the voltage, or the potential difference. However, we very often use that formula the other way around, where we have a charge at a high potential energy and we release it, and that potential energy gets transferred to kinetic energy. So very often we take this formula, we cross multiply and get Q delta V equals change in energy. And for an accelerating charge, the change in energy is 1/2 mvf squared minus 1/2 mvi squared, EF minus EI. You will hear me stress this a number of times throughout the course and at the end of the course as well. Don't assume that the initial kinetic energy is 0. Most of the time it is. When you see these problems on an exams, most of the time it starts from rest. And if it does start from rest, then VI is 0, which means this doesn't play a role, and you can just go Q delta V equals 1/2 mvf squared. But it's not always the case. And the other thing we learned is what 1 electron volt is. 1 electron volt is 1.6 times 10 to the negative 19 joules.
Please excuse the interruption. With grade 9 students with last names beginning with letters A through C, please come down to the office to get your photos. That's grade 9 students. If your last name begins with letters A through C, please to the office. Thank you.
I've also got in that little box the definition of 1 electron volt, but I also have just what 1 volt is. I think it's very useful to think of a volt as a joule per coulomb. I just think that's an important idea. So does anybody have any questions you would like me to go over from any of these problems? Ian?
9.
Okay, let's take a look at number 9. So how much energy is gained by an alpha particle that's accelerated through 15 volts? Now,
That's not the same one.
it isn't. All right.
Well, there's more to it. Sorry. Like a whole explanation.
You said 9, right?
Yes.
Is this not what your 9 says?
There's more to the question.
You asked about question 9.
Yeah.
This is question 9, isn't it?
Yes. Sorry. Yeah.
The stuff below it, I think, is for 10 and 11. Isn't it?
That makes a whole lot more sense. Could we do 10 then?
Okay. Does anybody want me to do 9? I want to speak briefly to it. There's 2 approaches here for question 9. One approach is to use your formula for potential difference. And I'm not going to write down the numbers, but I'm going to do the calculation. You're asked for the energy gained, that's this, which means I would take the charge times the voltage. So if I use this formula and I take the charge of an alpha particle multiplied by the voltage of 15 volts, this number that I get, everybody, is joules. Okay? This formula only is conversant in joules. It doesn't deal with anything else. Now, 1 electron volt, so that's how many joules. 1 electron volt is 1.6 times 10 to the negative 19 joules. I asked yesterday the question I'm about to ask now. And only 2 or 3 of you kind of nodded your head yesterday when I asked this. How many of you know what to do with this number of joules to get the number of electron volts? So more people are nodding now. It's becoming more obvious that you would divide this by this number. If it's ever unclear or you're ever unsure what you're going to do to determine a number of anything, electron volts, electrons, apples, oranges, monkeys, whatever, you set up a ratio. And the ratio here would be 1 EV is 1.6 times 10 to the negative 19 joules. That ratio is equal to x electron volts over this number of 4.8 times 10 to the negative 18 joules. Can you confirm when you cross multiply to solve that you get 30? You do. So the answer is right up there. It's 30 EV. Yeah.
For our written response question, would you want us to show our work like that? Ratio, or?
This would never be elevated to the status of a written response. If someplace in a written response you did have to convert joules to EV, you either have to do this or you have to write down 4.8 times 10 to the negative 18 divided by 1.6 times 10 to the negative 19. You need to show the calculation, but I don't think any real explanation is needed. Yeah. It's what I would call trivial. If you did have a written response, actually I'm glad you asked. If you did have a written response and you just went from this number to 30 and you didn't show it, I would probably ding you half a mark. But, okay, so it's 30 EV. We did not need to do any calculations here to know this, because an electron volt accelerated through an electron accelerated through 1 volt experiences a change in energy of 1 electron volt. An alpha particle accelerated through 1 volt would have to experience a change in energy of 2 electron volts, because an alpha particle has twice the charge. And when you look at this formula, charge determines the change in energy. The bigger the charge, the bigger the change in energy. And what that means is for every volt an alpha particle goes through, it gains 2 electron volts. So if it's 15 volts, it's 30. Anyway, you said question 10? Okay. So let's take a look at question 10. So we have a free electron. It just means an electron that's not attached to an atom. It has an initial speed of 2 million meters per second, and it's going to enter the region between the 2 plates. There's a whole bunch of information given here. There's the electron, and it's moving at that instant in time with this speed. You have to get used to the fact that sometimes these context boxes are used for multiple questions, and even if they're not used for multiple questions, you may be given extra information that you don't need. Okay? So we're given how long it takes to go from one plate to the next. We're given the distance between the plates. And the question is, what's the final energy of the electron just before it strikes the plate in joules? Well, this whole lesson was focused around potential difference equals change in energy over charge. So when you cross multiply here, Ian, you get the charge times the potential difference equals the change in energy. And we know what the charge is because it's an electron, and we know what the voltage is, don't we? Yeah, it's 200 volts. So we can calculate the change in energy. Now, if you look at this diagram, an electron is negative, which means if it has this speed of whatever, 2 million meters per second, and it's moving towards the positive plate, that kinetic energy that it has to begin with is only going to get bigger. It's going to gain energy, right? And that's borne out because if you take a look at this formula, we can go one step further. Q delta V equals EKF minus EKI. And I mentioned yesterday, I think Shannon, it might have been you were working on something, this whole idea at the beginning where we have this, just because you're given a situation where a charge is accelerated through a potential difference doesn't mean you're going to do this whole thing. You may not have to do the whole thing. What this question in number 10 is asking is, what's the final energy? Well, the final energy EKF will be equal to EKI plus Q delta V. And I'm not really going to do any calculations here. I'm just about done my explanation. I just want to say to you that this should make sense. What's the final kinetic energy? It's the initial kinetic energy plus this, which is delta E. This is the change in energy. You know, if you want to know my final bank balance, you're going to take my initial balance and add how much I deposited. So we're going to take the initial energy and add how much energy was deposited on top of that. And what you're going to have to do here then, Ian, is go 1/2 mvi squared plus Q delta V. I'm just capping that V to make sure you don't confuse it with this other V. And that will give you the answer. And since this formula that we started off with works only in joules and 1/2 mv squared gives you an answer in joules, this is going to give us the answer in joules. Yep.
Where did you put the EK final in the...
Well, it's equal. That's what we're calculating. So again, I'm not going to crunch the numbers here. You can do it on your own. Change in energy over charge equals potential difference. So if you cross multiply, you get this. This is kind of the starting point. This E is energy. So that means Q, I missed my delta here, but that's okay, equals 1/2 mv squared final minus 1/2 mv squared initial. You have enough information that you can calculate this thing, because you know the charge of the alpha particle and you know the voltage. You have enough information that you can calculate this thing, which means that knowing those two things will allow you to calculate this. You can take Q delta V and add 1/2 mvi squared. Once you have that energy will be equal to this yellow energy. Then you can multiply it by 2, divide by the mass, and then take the square root. Very similar to the question we just did, except the question we just did before, number 10, I believe, we stopped here because we just wanted to know that final energy. This time we go further and find the speed. Okay. All right, we're going to move on now. Can I get you to open up your books to the next lesson, which is Potential Difference Part 2. So what we're going to do today is work with potential difference and tie it into electric field strength between parallel plates. And in order to understand electric field strength between parallel plates, we have to compare different types of electric fields to begin with. And that's where we are starting. So I have 3 sources of electric fields here. The positive point charge source produces an electric field because if I put a test charge anywhere in this field, it's going to be influenced. It's going to experience an electric force. Okay? This negative point charge is the source of an electric field because if I put a test charge in the vicinity or in the space surrounding that source charge, that test charge will experience an electric force. It will be influenced. And there is an electric field between these 2 oppositely charged parallel plates because if I put a test charge in between those 2 plates, it's going to be influenced. It's going to experience a force due to the negative plate and a force due to the positive plate. Of course, the positive plate is on the left. I got that right today, right? Positive plate is on the left. So if you want, you can put some positives here and some negatives here. And we're asked to sketch the electric fields for each of the sources. Okay, remember, what you imagine putting in the field is a positive test charge. So what we're looking at here for this electric field is field lines that radiates away from the source. And the word radiate is kind of important here. I didn't draw them nicely spaced. If that's a worry to you, you can space them out a little better. So again, this is because I imagine putting a positive test charge in here. An imaginary positive test charge will be forced away from the positive source. Similarly, if I put an imaginary positive test charge in the space surrounding this source, the lines radiate away, but the arrows point towards. It's still kind of the same shape, it's just that the direction is opposite. And if I were to put a positive test charge anywhere in the region between these two oppositely charged parallel plates, two forces are going to be acting on that positive test charge. A positive test charge placed in the middle of the plates will be forced away from the left plate because it will be repelled from the positive, and it will be attracted to the negative, which means the electric field direction will be this way. And this is what the field ends up looking like. The big difference here is that the lines are all parallel. And because the lines are all parallel, they're equally spaced. So if I were to talk about just the location in space, I'm not even worried about a positive test charge or anything. If I were to just talk about the electric field at that pink point and compare it to the electric field at this blue point, the electric field at the pink point is stronger because the field lines are closer together. And I think we know it's stronger at the pink point because you're closer to the source. But in terms of field lines, it's stronger at the pink point. The electric field is stronger because the field lines are more dense. There's a field density that's greater. Similarly over here, whatever the field strength is here, it's going to be greater than the field strength here, because the lines are closer together. But when we talk about different locations here, the field strength is the same everywhere. It's the same everywhere because the distance between the field lines, or the field density, is the same. And some of you might, make the argument that since this is closer to the negative plate, there's more of an effect. But don't forget, the field in here is produced by two influences, the positive plate and the negative plate. So at this point, the positive plate has a huge influence on a charge in the field, and the negative plate doesn't have much. But at this point, the opposite is true. And as you go from one plate to the other, it balances out. So that's important in answering B. Compare the fields in 3, or the field in 3 to the fields in 1 and 2. First of all, we call these fields radial. And it's like when you look at the spokes on a bicycle tire. They radiate away. They form radii. So those lines are either pointing away from the source or towards the source from a number of different directions. The word we use that's kind of comparable to the word radial is uniform. Uniform means constant. I mean, when you talk about uniform motion, it's constant velocity. When you talk about uniform acceleration, it's constant acceleration. So a uniform field means it's a constant field everywhere in there. The key idea here, though, is that the electric field depends on the location. Remember, we just spent some time over yesterday and today talking about E being energy, but E with a vector symbol is electric field. Okay? And by the way, when I say E with a vector symbol depends on the location, I'm saying the magnitude of the field and the direction of the field. Because when I go back and I take a look at these 2 points in space, not only is the electric field at pink larger in magnitude than the electric field at blue, but the electric field at pink is in a different direction. The electric field at pink is this way, the electric field at blue is this way. So everything is different depending on the location. Whereas when you take a look at field 3, the electric field depends on, I don't want you to say nothing. I know the electric field is the same everywhere, but I'm asking you a different question now. What do you feel you could change in that third electric field diagram to get a different electric field? Sure, and that's an intuitive thing, and I'm glad you said that. If I were to move the plates closer together, what effect do you think that would have on the electric field? It would, and it turns out you're right, it would increase. The field lines, if I take those two plates and I move them closer together, you'll get more field lines. They'll be closer together. And again, that's kind of an intuitive thing, and I don't think I will ever really explain non-intuitively why that's the case. Okay? Is there something else you could change about that source to get a different electric field without changing the distance between the plates? Ian? The voltage. Okay. So if we go back to this, it's the distance to the source and the source that determine the electric field. When we look at this, it's the distance between the plates and the voltage that determine it. So I'm going to put here depends on the voltage and the distance between the plates. And I might as well tell you this because whenever I teach this, very rarely does somebody come up with this distance thing, but Annalee did, so we're going to include it here. We say delta D for distance between the plates. I don't like it, but whenever you see two parallel plates, we call it delta D, the distance between them. Over here depends on the location, which is R. It also depends on the charge of the source, right? I mean, we didn't really talk about that till now, but if I take that positive point source and I make it a larger source, a larger charge, you're going to get a larger field strength. And incidentally, while we're here, the electric field here has a magnitude that can be calculated using this. Remember that formula from a few lessons ago? Okay. There it is. The electric field depends on the charge of the source and the distance. You don't know this formula yet, but you're going to learn it in about 10 minutes. Okay. All right. Let's take a look at the next part of this question. A positively charged object is placed in each of the three electric fields and released. Okay? So what we're imagining happening here is we are taking a positive object We are taking a positive object and putting it in each of the fields. I could ask this question with a negative object instead. This has nothing to do with positive test charges. But I'm just saying we put a positive object in each of the fields. And we release it. And I hope you understand in each of these cases the charge is going to accelerate. Because it's going to experience a force because you're putting it in the field, so it will accelerate. The question is, what will happen to, I'm going to come back to that. I'm going to start off with the force experienced by the charge. Take a look at your positive object put in field 1. Which way will it be forced? Towards the source or away? Away. So it's going to experience a net electrical force and it's going to accelerate, but it's going to be moving away, which means the amount of force it will be experiencing will decrease. Because it's going to be further away from the source. So what's going to happen to the force acting on the charge is it's going to decrease. It's still going to accelerate, but it's going to accelerate at a lower and lower rate. So if the force experienced decreases, then the acceleration must decrease. What happens to the strength of the electric field that that charge is in? Well, it goes from here it goes from perhaps here to here. And the final location is further away and the field lines are further apart, and that means that the electric field it finds itself in is less. And this all makes sense with equations, because if you take a look at the formulas, the acceleration is related to the net force, and the net force is related to the field. So if the field lines are further apart, you'll get less force. If you get less force, you're going to get less acceleration. These things are all intertwined together. And with that in mind, we can certainly answer about field 2. Because if I put my positive charge that's in this question in field 2, it will accelerate because there's an electric field producing an electric force. But that electric force is going to grow because the force is in the direction of towards the source, which means that positive charge is going to get closer to the negative source, and Coulomb's law says the force will be greater. Or closer to the source, the field lines are closer together, stronger field means greater force. Greater force or greater field means greater acceleration. Now, what's going to happen to the amount of force experienced? Well, we'll do the field first. What's going to happen to the electric field as this positive charge moves from here to here? Well, the electric field is going to stay the same because the field lines are uniform, they're parallel. And if the electric field stays the same, then the electric force will stay the same. And if the electric force stays the same, the acceleration will stay the same. So for all of these, we can say that the quantity will remain constant. Now let's talk about the energy. We had a discussion the other day, it might have been yesterday, about potential energy and what it means. Potential energy exists if you can imagine that there's something kind of wanting to move away from the current state. So if I put a bow, an arrow in a bow and I pull it back, I can feel some resistance there. So if I let the bow go or the arrow go, the arrow takes off. If I, hold this book above the floor, I can feel it wanting to go down. So when I pull my hand out, it's going to move towards the floor. In all three of these cases, everyone, in all three of these cases, if I'm holding this charge here somehow, without grounding it, I can feel it pushing away from the source. If I'm holding this charge in field 2 here, I can feel it being pulled towards the source. If I'm holding a charge in between the plates, I can feel it, if it's positive, being pulled to the right. So these all have potential energy. But when I release all of them, because they all have potential energy, then what is going to happen is they are going to speed up. I mean, just look at the fact that there's an acceleration. All of these things, you want to be very careful here, all of these situations involve an acceleration. The fact that the acceleration may decrease or increase or remain constant doesn't change the fact that acceleration means speeding up in this context. So that means the kinetic energy must go up, and that kinetic energy has to come from somewhere, and it comes from a loss in potential energy. And keep in mind, we're done with this question now, but keep in mind I could have said instead, a negative object is put in each field. What happens? That would change some of your answers. Does anybody have any questions with that part of this question?
You say that the strength of the electric, the field itself is not changing, just the strength.
Well, if the strength changes, the field changes.
The force.
Just a second. Just a second. I'm not saying that this picture changes. I'm saying at these two places in field 1 where I have the 2 pink dots, the field is different. It has a different value at those 2 points. The field here has a certain number of newtons per coulomb away from the source. The field here has a different number of newtons per coulomb away from the source.
So the field can change, but what are they both in then?
They're in this field. But this field covers a space. So if I talk about the magnitude of the field at one point and the magnitude of the field at a different point, they're different electric field strengths. They're different electric fields at those points. I think you're overthinking things here. The field is the whole thing. What we're talking about increasing or decreasing is the value of the field. Okay. Any other questions before we go on? All right. So I told you, I'm going to go back to this. You can turn the page. I told you that, fields 1 and 2 have this formula, which shows that the field strength depends on the source charge and the distance. And then I've told you, Annalee figured out intuitively that if the distance between the plates is smaller, you get a stronger field. And we didn't actually say this, but I think it's reasonable to say if the voltage is greater, you get a greater field. Okay. I want to make sure I said what I meant to say. Did I just say that if the distance is smaller, you get a greater field? Okay, that's good, because that's what I meant to say. So you can increase the field in parallel plates in that situation by cranking up the voltage or moving the plates closer together. And it turns out that this is the formula for that specific situation. If you take the voltage between the plates and divide by the distance between the plates, you will get the electric field strength between the plates. Now, we know that electric field strength is newtons per coulomb. That's the set of units. I'm telling you that it's also volts per meter. And this is very similar, everybody. I don't want to I don't want to spend too much time here on this, but it's very similar to the fact that impulse and momentum have two different looking sets of units, but they are the same equivalent set of units. A volt per meter is the same as a newton per coulomb. And I'm not going to explain that today. Probably tomorrow. Yep.
I thought volts could also be newtons per coulomb.
Yes. So volts could be newtons per coulomb, right? And that means volts per meter are this. No, Ariana. A volt is not a newton per coulomb. What's a volt? It's a joule per coulomb. So that means that you could have joules per coulomb meters also. And I might as well do this now that you brought it up. A joule, since energy is a half mv squared, no, I'll do it this way. Since energy is work, which is force times distance, a joule is a newton times a meter, isn't it? So I'm going to put a Newton times a meter here. And I will get a Newton times a meter over a Coulomb times a meter, which is a Newton per Coulomb. So it's all consistent. Okay. All right, so in this formula, delta V is obviously voltage, delta D is the distance between the plates, and E is electric field strength. So let's do a couple of problems. An alpha particle which is initially at rest accelerates between two oppositely charged parallel plates. The distance between the plates is 2 centimeters, and the voltage is 175 volts. Find the acceleration experienced by the alpha particle, and I want to confine us to physics 30 ideas here, not kinematics. Okay? And also find the final speed reached by the alpha particle. Well, what I hope you get out of any question that says acceleration is F net equals ma. Right? If you want to find acceleration, you need the net force. But in this particular case, the net force is the electric force. Now, I don't want to rush through this. Electric force equals Q times E, and that's a rearrangement of this equation in the middle of your screen right now. It's been a while, a few days since we've used this, but remember, force equals property of matter times field. Electric force equals electric charge times electric field. And since this alpha particle, an alpha particle consists of 2 protons and 2 neutrons, since this alpha particle is only being influenced by an electric field, if I were to draw a free body diagram on this, that's the only force. I may be oversimplifying things, but I think fundamentally this idea is important. Since that's the only force, it's the net force. So I can write F net is equal to Fe. And I'm going to be very picky here by adding one other layer on top of this explanation. I'm not saying there are 2 forces that happen to be equal. There's one force. And you can call it the electric force or you can call it the net force. So how do we calculate F net? It's ma. How do we calculate the electric force? It's QE. I'm going to drop the vector symbols at this point. So we know the mass because it's an alpha particle. We know the charge because it's an alpha particle, but we don't know the electric field strength. However, we can calculate the electric field strength using our newfound formula, voltage over distance. It's voltage between the plates over distance between the plates. So 175 volts divided by 0.02 meters is it 87,500? 8750? Okay. So you get 8750. The electric field strength is 8750 volts per meter. And we don't want to, at this stage of the game, try to figure out where we're going to get the right units from. It all works out, okay? So I put in the mass of the alpha particle, which we all know is 6.65 times 10 to the negative 27. And if you don't, you look it up to remind yourself what it is. Times the acceleration equals the charge of an alpha particle, which is 2 elementary charges, times the electric field of 8750. And then we solve for the acceleration. And I know that you could do this in pieces. You could calculate the electric field, and then calculate the electric force, and then calculate the acceleration. But I would like you to start putting things together. And in fact, I hope some of you see we could have done this. We could have just substituted voltage over distance in there. So can everybody calculate an answer for me, please? And Jack, will you let me know when you have it? We're just calculating the acceleration here. You got it? What is it?
4.2 times 10 to the power of 1 times 10 to the power of 11.
4.2 times 10 to the 11. Anybody else up for that? Okay, good. Part B says, what's the final speed reached by the alpha particle? Well, I'm just trying to keep you on your toes here. The initial speed is 0. Starts from rest, doesn't it? Well, this is a q delta v equals a half mv squared situation. I told you yesterday that this is a calculation. Since there's no initial kinetic energy, we don't have to write minus vi, 1 half mvi squared. I told you yesterday, this calculation, this particular one, we're going to be doing like 50, 60 times. It's so common. All you have to do is take the charge times the voltage times 2 divided by the mass and then take the square root. It's something that you shouldn't even really need to think too much about by the time we get to the end of the course. So we know it's an alpha particle. We know the charge. The voltage was 175 volts. We know the mass of the alpha particle. I know sometimes I kind of push you, but I need you to be able to do this calculation fairly naturally. The charge of an alpha particle times the voltage. We need to multiply that by 2. We need to divide it by the mass. And then take the square root. I just took the square root by raising it to the power of 5. You can use your square root function. But I get 1.3 times 10 to the 5 meters per second. Do you get the same thing? Okay. All right, let's take a look at the final example. We're not going to do, I don't think we're going to do 3. I think I'm in a bit of a pickle here, because if I do 3, you're going to have hardly any time to practice this. So at the beginning of tomorrow's class, can you flip the page? Can I see what the next lesson is? One more. Yeah, we'll be able to do number 3 tomorrow with tomorrow's lesson. So an electron accelerates from rest in a uniform electric field of 4,500 volts per meter. And the plates are 12 centimeters apart. What's the final speed of the electron? When you're dealing in this course with acceleration, you think net force. When you're dealing with charges and final speeds, you want to think in terms of voltage. I need you to understand something here. I would really hope that you understand something. Knowing the voltage that a charged particle is accelerated through allows you to find the speed it reaches. Are you with me on that? That's this calculation that we did at the bottom for B. It's just a natural thing. It's something we have to be able to do. So how can we find the voltage that this accelerates through? Well, you know the electric field strength. And that's E for electric field, is voltage over distance. And if you know the electric field strength and the distance, you can multiply those two things together to get the voltage. And if you know the voltage, then you're going to do the Q delta V equals 1/2 mv squared, so that you can put the voltage in to get out the speed. And I apologize because I very often write this, but really this is this equation. This E is energy. It's this equation reworked to get this. It's this equation turned into Q delta V equals change in energy, which is change in kinetic energy, which is final kinetic minus initial kinetic, But if it starts from rest, the initial kinetic is 0. So we get this. And again, I want to caution you, it's this because it starts from rest. Okay, well, let's find the voltage. The electric field strength is 4,500 volts per meter. That equals the voltage over 0.12 meters. I want to say 500 and, no. Yeah, I want to say 540. 540 volts. And again, I'm not going to write this down. This is like, we've used this calculation or this formula like 4 or 5 times already today. We need to become very familiar, very friendly with this formula, know how it works. So I'm going to take the voltage. Is it an alpha particle? No, it's an electron. Always check. Very easy to use the wrong information. So the charge of an electron multiplied by the voltage of 540, multiplied by 2 to get rid of the half, divide by the mass of the electron to get rid of the m, then hit equals, then take the square root. So 1.4 times 10 to the 7 meters per second. Incidentally, Ariana and other people, you might be interested, in this question, we had enough information to find the acceleration. You certainly could have done that here. Because you have the field. If you multiply by the charge, you get the force. If you divide the force by the mass, you get the acceleration. Then you can use VI as 0, the acceleration and the distance, to find VF. And this actually goes all the way back to your question before. Could we have done that other question that way? The one you had asked about at the beginning. So I have a feeling what's going to happen is there's going to be a couple of questions in this practice assignment that rely on your understanding of example 3. And we may not even have to do example 3 tomorrow because I suspect some of you will have questions about some of the assignment problems. And I'll be able to teach you what's involved in number 3 as we go through them. So you're practicing these problems for tomorrow. Does anybody have any questions? Ariana? It's a good question. The question is there ever a time where we put a negative with the charge? You're not talking about a negative exponent. You're talking about a charge being negative. When you put a negative with a charge in any formula, and the answer is never. Never. Your textbook will, and it tries to be clever and come up with some neat little rules. So if you're looking at your textbook, don't do what they're doing. Okay. All right, get to work, please.